Here's our high-level WAN design. We'll wrap our existing 6Q campus policy inside of a traffic conditioning policy with multiple shapers. Each shaper will match traffic to a specific remote site, granting 35 megabits per second of committed bandwidth to each. The spokes will utilize this shaping rate upstream as well, but don't need to match any destination IP addresses in that direction. There isn't any new technology here, but we are deploying our existing tools in a unique way. Sometimes it's a good idea to build your traffic conditioning policies before your queuing policies. Let me demonstrate why. Let's begin by exploring the classification process, which includes class maps and access lists. While classifying traffic for the purpose of marking it with a DSCP value is commonly done on ingress near the endpoints, you can also classify traffic on egress. These two class maps match R15 and R16, and all WAN traffic destined to those sites will match the proper class map. Looking at the ACLs, they simply permit all IP traffic towards those tunnel endpoints. You can also see matches under the ACL, indicating that the policy is already applied and probably functioning correctly. Let's see how these class maps fit together by reviewing the WAN shaping policy map. This looks a bit different than your classic queuing and shaping hierarchical policy. Rather than wrapping a queuing policy under class default, we use individual 35 megabits per second shapers for each remote site per the design requirements. This means R15 and R16 can each download up to 35 megabits per second from the GlobalMantic's main site, which includes backhauled internet traffic. What's up with those BC and BE values, though? Let's assume the MPLS carrier is very strict with its ingress policers and does not allow bursting at all. This may not be true, and many carriers can't even reliably tell you if they do or not, so let's play it safe. We'll use 4 milliseconds as our shaper's TC to optimize voice performance. Working out the math, 4 milliseconds times 35 megabits per second yields 140 kilobits or 17.5 kilobytes. Because bursting is completely disabled, GlobalMantic cannot reclaim any lost time intervals after periods of silence, so let's use 0 for BE to disable bursting. Always double check your work. Here's a screenshot of my spreadsheet tool confirming that our calculations are correct. Next, let's discuss overhead accounting. When you apply traffic conditioners on egress, which are often shapers but could also be policers, the final layer 2 encapsulation has not been computed yet. This is due to the QoS order of operations in most routers. On egress, you can account for this overhead manually. Given a policed CAR of 35 megabits per second, we must either shape to a number less than 35 megabits per second or properly account for the 14 bytes of Ethernet overhead. This includes the 6-byte destination MAC, 6-byte source MAC, and 2-byte ether type. If a VLAN is used, add another 4 bytes, resulting in 18. As a quick side note, the shaper does correctly account for GRE and IPsec encapsulation because we applied the policy to the physical interface, not the tunnel interface, which is the right spot for it. This means our implementation is correct so far. Notice I haven't added our queuing policy inside the shapers yet. We'll do that soon, but from an implementation perspective, it can be useful to configure your shapers and policers before your queuing policy. This allows you to verify that your traffic conditioning is correct on a macro level. Let's quickly examine the policy statistics. We already see matches under both policies given that the WAN tunnels are already up and user traffic is flowing across the network. A quick glance at our CAR, BC, and BE indicates we've configured it correctly. We also see a note about overhead accounting being enabled, although the command doesn't reveal the 14-byte value we entered. To double check that the policy works, let's send 100 packets to R15's loopback from R8. I'll quickly issue the 3 commands shown. The first one will print out the current packet counters so we have an updated reference. Then we'll send 100 pings. Finally, we'll confirm the difference by checking the counters again. After sending 100 packets to R15, we can see the number of packets went from 692 to 795, an increase of just over 100 packets. If you account for some network control in the background, this looks like a proper match. Let's repeat the exact same process except targeting R16. After sending pings to R16, we observe a difference of roughly 100 packets as we expected. This form of rapid, manual testing is a good way to ensure your per-site classification and shaping is working. As a final point, let's check out R15's QoS configuration. At a high level, we have our standard classification and marking policy applied to the LAN side of the router. Upstream towards the carrier, we have a WAN shaper, so let's dig into that. It's the same shaping configuration we saw on R8, except we don't need per destination matching since the WAN is only hub-spoke. Inside of it, we reference the common queuing policy, allowing the router to transmit upstream traffic according to GlobalMantic's priorities. Coming up next, we'll perform this reference at the hub.